All right. This is the third subject in the discussion of one-dimensional analysis. So make sure that I'm using a significant amount of time for the discussion of one-dimensional analysis. The reason that I'm doing this is that if you understand the one-dimensional problems in every point, then you can easily extend your understanding to two-dimensional problems and three-dimensional problems, even to continuum problems. Okay, that's why understanding one-dimensional problem is very important. All right, the subject that we want to discuss here is statically indeterminate structures. The statically indeterminate structures is called in 우리말 부정정. 부정정 구조물. So what if the statically determinate structures? Statically determinate structures. They are called 정정 구조물. Okay, 정정 구조물. Then what is the difference between these two systems? Okay, according to our textbook, the definitions for the statically determinate structures are given in this way. So all the reactions and the internal forces can be found or can be calculated by using only the equilibrium equations. That is the definition of statically determinate structures. And then let's look at the statically indeterminate structures. According to the definition in our textbook, the number of unknowns are greater than the number of equilibrium equations. So all the three conditions are to be considered to close the analysis. So what does it mean actually? So let's look at this. Here we don't know what. So we have one unknown here, reaction, isn't it right? One reaction. So then if you use equilibrium to calculate the reaction is what? We can easily determine the reaction. The sum of P1 and P2 should be equal to the reaction, isn't it? So we don't need other conditions to determine the reactions. But if you look at the second example, we have two reactions because the bottom and the top ends are fixed. That's why we have the reaction at point A and the reaction at point B. Because of this, but we can use only the equilibrium equation in the vertical direction. That's why we cannot determine the reactions with only the equilibrium equation. Okay. So let's try to understand this problem differently using this diagram. So force and stress and the strain, and then the displacement. This is the flow of analysis, right? So in the case of statically determinate structures, then you don't have to worry about the use of the displacement compatibility. So to understand the stress field, actually, to design a structure, we need to determine the stress field. So we use only the force equilibrium, and then we can determine the stress field. And then we can understand that this is the character of the statically determinate structures. Okay. And how about the statically indeterminate structures? The statically indeterminate structures is not something else, okay? It's not something else. That represent just general structures. In the case of general structures, so we cannot finish our analysis by using only the force equilibrium. So, but we have to consider, all of the three conditions. And this is the case for the statically indeterminate indeterminate structures. Do you understand the difference? Okay. Alright, so now let's discuss a simple example to understand the nature of the difference between the statically indeterminate structural systems and statically determinate structural systems. Okay, so I want to consider this example. So this example is given here. The next slide. So let's consider first example. Okay, so to understand this procedure, I want to consider, I want to try to solve this problem by using these three equations as given in my lecture note. Okay, so first we need to idealize the structure, isn't it right? So we have a support here, and then we have this one-dimensional systems, and then this point is denoted by A, and here C, and then B, and then I have a concentrated load at point C. Okay, this is my structural system. So here, because point A and point B are fixed, that's why there must be some reactions. So R, by the way, sorry. We must have some reaction here, okay? Reaction. So RB. And then a point A is also fixed. That's why there must be another reaction, RA. Okay. So now, before our analysis, we have to introduce a coordinate system, isn't it? That's the real first step. Otherwise, we cannot start our analysis by using, numeric values. So that's why to do so, I want to use this coordinate system. So X coordinate system. So if you don't like to choose point A as the origin, you can choose point, if you don't like to choose point B as the origin, you can use point A as the origin, or you can use a downward coordinate system. That doesn't produce any different result. Your solution must be completely same. Okay, trust me. Okay, then if you did, then first we have to I want to use what the displacement. I want to define the displacement field first. Okay, displacement field. So my displacement field is what? Then my displacement, change of my displacement with respect to X coordinate. Then this is my X-axis, isn't it? So make sure that point B is fixed. That's which means the displacement at this point should be equal to 0, isn't it? And then how about at point C? This is point B and point C. At point C, we have displacement, nodal displacement UC, but we haven't determined the nodal displacement. Okay, we don't know that. Okay, but we know there exists some abnormal nodal displacement. That's what you know. And how about at point A? Point A, UC is because point A is fixed to, that's why this is my nodal displacement. This is equal to 0. This is point A. So then I can introduce the change of what the displacement field, because we want to consider prismatic bar, which means there is no change in the cross-sectional area between two nodes. That's why we can draw a straight line between these points. Okay, this is our displacement field according to the displacement compatibility. Okay, for general discussion, then instead of talking about zero nodal displacement at point A and point B, let's try to consider non-zero displacement. So we want to consider nodal displacement later. That doesn't produce any difference, okay? Instead of talking about instead of using the non-zero zero nodal displacement, so we want to consider non-zero nodal displacement, okay, for generality. So here we may have nodal displacement UB, this is point B, and this is point C. We may have what, nodal displacement UC here, and then we may have non-zero nodal displacement at point A. This is given by UA. Okay? And then because of the argument for prismatic bars, so we can draw with the same elastic modulus, we can draw a straight line, okay, to measure the strain. So once I have this displacement field, so can you measure the strain field? Yes, we can measure the strain field. So how do you measure the strain field? Now I'm here. Now I'm here. So let's try to calculate the strain value. Okay, now I'm here. If I calculate the strain value, my strain in BC segment can be calculated as what? Please note the definition of strain. The change of displacement with respect to the coordinate, isn't it? That is the definition of the strain. So if you consider this, and then because this is the change of the direction of my coordinate, so we need to calculate the displacement, we need to subtract UB from UC, isn't it? It's UC minus UB. And then should be divided by the length, isn't it, right? So I want to consider, okay, so I forgot the length here. So for example, I want to consider this is L, how do I want to say? So LBC, for example. And then also we want to consider this is LAC. So it should be divided by LBC, okay? LBC. Simply speaking, we subtracted the nodal coordinate of point B from nodal coordinate of point C. Now that is equal to the length of the BC segment. And then here, how about the strain of AC segment? Strain of AC segment, similar to this, we need to consider UA minus UC, isn't it? And then divided by the length of AC segment. So again, so we use length in the denominator because, implicitly we subtracted the coordinate of point C from the coordinate of point A, okay? That's why the numeric value is equal to the length of AC segment. So basically, but we always make sure that we need to deal with the coordinate, okay? All right, so here now let's consider the boundary condition. We can save out our labor. So here, if you consider boundary condition at point A and point B, the displacement is equal to 0 at these 2 points. That's why we need to drop the nodal displacement here and the nodal displacement B. Then my strain becomes very simplified, isn't it? So then what's the next step? The next step is, so we need to calculate the stress value. Okay, this is the next step. So we need to calculate the stress value. So how do you calculate the stress? Yellow colors. The visibility of yellow color is not that good. Let's use black one. The stress of BC segment is equal to what? The elastic modulus of BC segment times the strain of BC segment. This is equal to elastic modulus divided by, since we have the length here, and then times UC, nodal displacement UC. And then how about stress of AC segment? This is equal to elastic modulus of AC segment. We may consider different elastic modulus for different segments, and then this is multiplied by the strain of AC segment. This is equal to minus is elastic modulus divided by the length of its segment times the nodal displacement UC. Got it? So now we are here, and then what's the next step? The next step is we need to check the force equilibrium. We need to check the force equilibrium. Okay, we need to check the force equilibrium. Next step is we need to check the force equilibrium. Okay, force equilibrium. So let's check the force equilibrium. To check the force equilibrium, so I need to choose, the free body diagram to check the force equilibrium. But make sure that the reaction is unknown here, because reaction is unknown, which means even if you choose this free body diagram, so that involves another unknown. That's why we can finish our analysis. So also this point too. Okay. And then that's why I'd like to choose this free body diagram. Okay, the whole system. So let's consider this free body diagram. If you consider this free body diagram, then I have force P at point C. And then here we have the normal stress, sigma, because I'm talking about AC segment, AC. So, or we have normal stress downward. So which one is correct? So upward or downward? Which one is correct? Upward traction or downward correction? Downward traction as the default choice. And how about here on the side of BC? We need to consider the normal stress BC here, or normal stress BC downward. So which one is correct? So let's do a quiz. This is option A and option B, and the C and D. So what are correct solutions? The combination of A and D, or combination of B and C, or combination of A and C, or combination of B and D? Which one is correct? Just give me your opinion so that I can check if you understand correctly. Okay, 진영이 B and C, B and C, B and C. So and what else? And then 유준이 A and C, A and C. And then 우철이 B and C. And then good response, 창현이 A and C. And then 진우 B and C. What? And then 석주 A. 석주, we need to play with a pair. 호준이 A and C. 석주 A and C. 석주 A and C. Anything else? Nobody's correct. So make sure that the default, default positive of normal stress is that any stress field which stretches the material, okay? Then this is a default positive. The stress is different from the forces, okay? So we'll discuss the nature of stress later. 호준이 UU is not a right solution. Anything else? 경환이 B and D. 뭐? 우철이 A and D. Yes, A and D is correct, okay? A and D is correct. So as I told you, the default positive of stress condition is if the material, if the stress stretches the material, then this is the default positive choice of normal stress. That's why here we need to consider this, okay? We need to consider this and this, okay? This is not a right pair. Okay, so now let's check the force equilibrium in the vertical direction. So I want to check the force equilibrium in the vertical direction. Let's check the force equilibrium in the vertical direction should be equal to 0, because I'm talking about a system in equilibrium. The sum of force acting on this free body should be equal to 0. So the first part on top of the structure system is what? I have sigma AC and then multiplied by the cross-section area of that segment AC, and then its direction is what? Its direction is upward, isn't it right? So in the upward, according to the choice of this coordinate system, upward is positive, okay? And how about now that we need to consider the external force. The external force is minus P. The reason is this is the default, the local coordinate system for checking force equilibrium. And then we need to consider this guy, right? Also this guy is heading downward. That's why we need to choose minus sigma BC and then area of BC segment. So they should be equal to 0. So now we can finish our analysis. So we have the information of the normal stress here. We have the information of normal stress here. And then we have information of normal stress here. So let's plug these two expressions into this equation. Okay. So here, sigma AC is given by this equation. That's why minus elastic modulus of AC segment and the area of AC segment divided by the length of AC segment times nodal displacement. And then let's consider the last term. And this is equal to minus elastic modulus of BC segment. Make sure that we have minus sign here. And then the cross-section area of BC segment divided by length of BC segment. So I have nodal displacement UC is equal to applied force P. So now can you determine the nodal displacement? Yeah, so you can determine nodal displacement very easily. So we have only one equation and with only one unknown. So we can finish our analysis. Okay, we can determine the nodal displacement. So once you determine the nodal displacement, so we can determine the normal stresses for these two segments. Then once I have nodal displacement, also I can determine the strain distribution. So now let's talk about how we determine the reactions. Look at this. Since I'm using this coordinate system, so I have to choose a default the direction of my reaction, because this is upward positive. That's why I want to choose this is the direction of the reaction. So make sure that the reaction is unknown, okay, unknown yet. So I want to choose the default direction of the reaction. So now let's check one by one. Since we just finished our calculation for the information of normal stresses, so now we can determine the reactions using the force equilibrium for this free body diagram and for this free body diagram. Okay, let's talk about the first free body diagram. So I'm talking about this one, okay, to determine the reaction at point A. Okay, so let's consider the first part. This is point A, and then we have this reaction, the unknown reaction. And then if you look at here, there exists some normal stress too, isn't it? Because I'm talking about AC segment. This is equal to the normal stress is what? Sigma AC. So make sure that we can determine sigma AC because we just calculated nodal displacement. So let's check the force equilibrium for this body. Then we can determine the magnitude of a reaction. So make sure that I'm not talking about the reaction force. So I'm talking about the magnitude of the reaction force, okay? Which means 크기, okay? Its direction is given here. So we already assume a direction. So its magnitude is equal to sigma AC times its cross-section area. Okay, let's visit the information of the normal stress is here. This is equal to minus length of AC segment, elastic modulus of AC segment, and then its cross-section area multiplied by nodal displacement at point C. Okay? So can you work for the reaction at point B? So we can do the same thing here. So at point B, again, we have a reaction. This is point B. Reaction at point B, point B. And then we need to consider the distribution of normal stress. Make sure that the default direction of the normal stress is to way of stretching the material, sigma BC. Okay? So in this case, because they are heading in the same direction to satisfy the force equilibrium for this small body, the only way to satisfy is what? The RB is equal to minus sigma BC times area of the cross-section area of the BC. And this is equal to, where's the information of sigma BC? The information of sigma BC is here, okay? So this is equal to minus elastic modulus of BC, and then cross-section area divided by length of the BC times UC. So this is the finish of our analysis for this statically indeterminate structural system. Do you have any question here? So if you don't have a question, let's try to solve this problem in another way, okay? So now here to use, so this is called so-called compliance method. in 우리말 유연도법, 유연도 방법. In English we call it compliance method. Or actually, personally thinking, the compliance method is not, it does not count the nature of this method. We have to say that compatibility method. Compatibility, that's better. Okay, so let me explain you how we approach this problem using this method. So key point in this method is we want to use only, we want to consider the structure system as a combination of multiple the statically determinate structures, okay, to represent the original system. And the second, so we'd like to assume the superposition. Okay, superposition. So look at this. So as long as we deal with a linear system, for example, let's consider a linear system. Let's say this is y and x. So y is function of x. Okay, since this is straight line, we call it linear system. So let's consider x1 here and also x2. Okay, so if you put x1 to this system, then we should get y1 here. This is the consequence of the linear system. And then if you put x2, then we can get y2. Okay, so what I mean, we can get y1 for x1 and the y2 for x2. But what if we put x1 plus x2, for example, so let's consider this here, this place. This is x1 plus x2. Then because of nature of linear system, the response y for x1 and x2, because of nature of linear system, this is equal to fx1 plus fx2. Okay, and this is y1 plus y2. Okay, so what does it mean? To deal with this complicated system, so we don't have to work for this complicated system. Instead of that, so we deal with simple individual systems and we superpose them to represent the overall behavior. This is the key point regarding the principle of superposition. So now let's use the principle of superposition. Okay, so now this is the system. Certainly this is a statically indeterminate structural system. Okay, and then I'd like to decompose this structural system. Force P, and then I have reaction R A, and then here RB, isn't it? And then I'd like to decompose this structural system into two. The first, system 1, okay, system 1, and then plus system 2. Okay, system 2. And then here we want to consider the external load P. Okay, external load P. And then, which means because we have external load P, there must be a reaction here. So this reaction, this is we would like call this is a reaction at point B, but for system 1, okay, for system 1. And then here we want to consider a unit node. I want to consider unit node 1, unit node 1, okay, unit node 1, because we don't know the magnitude of reaction. And then here we must have the reaction, say the reaction, but in this time, because now I'm working for system 2, okay, system 2. And then because we don't know the magnitude of reaction, so I need to multiply, the magnitude of the reactions, RA, the actual RA. So let's consider one by one. Then let's consider the bottom part. Let's look at the bottom part. If you look at the bottom part, so let's check the reaction only. If you check the reaction, so RB is equal to RB of system 1 plus RB in system 2, okay? And then multiplied by the actual RA in the system, okay? According to this principle, isn't it? According to this principle, linear superposition, the characteristics of linear system. So how about here? And if you look at the middle point, so middle point, let's look at the middle point. Then the P, downward P, is equal to downward P plus, there is no external force here, 0 times RA. So make sure that the overall structural system of system 2 is scaled by RA here, okay? So this is the same, okay, same. And how about point here, point A. So let's look at point A. If you look at point A, yeah, so let's look at point A. So if you look at point A, RA is equal to, there is no force here at this point, 0 plus, and then unit load plus RA, okay, same. But how about the displacement now? This is for the forces, okay? So according to my diagram, so we need to consider the force and the stress and strain and displacement, okay? So we just check the forces. Then now we need to check the displacement. So now let's check the point B. If you look at the point B, you know, point B is already fixed, isn't it? Already fixed. That's why displacement at point B is equal to 0. We don't have to worry about it. And how about point A? How about point here, the middle point? Well, we are here, we must have non-zero displacement, and also here. That's why it is very hard to recognize. And then how about look at the point A? In the case of point A, the displacement at point A is actually, it is equal to 0. And then I have non-zero, so non-zero, isn't it? Plus, I also have non-zero system 1 plus the non-zero displacement, the point 2 times RA, isn't it? So which means here I have one equation. So we can calculate the displacement here, okay, displacement here. And then also I can calculate displacement at this point. And then because I have one unknown, then I can determine the reaction very easily, isn't it? So even in this method, so anyway, we have to use the displacement compatibility to calculate the displacement, okay? So that makes the procedure for the calculation becomes, you know, very complicated. That's why I prefer to use the second pass. I just start from the displacement, the definition of displacement field, and then I calculate the strain and the stress, and then I finish my calculation checking the force equilibrium. So as given in the textbook, so you can follow the procedure given for this 유연도법 compliance method. There's no difference. You should get exactly same result, okay? So what you have to pay attention to is, so we have to recover the original system if you superpose. So make sure your structure system, here there's a very important point you have to keep in mind is our structure system doesn't include, when you consider the superposition. So you have to define your structure system. My structure system is here, okay? This is my structure system. So I didn't shade the support intentionally. It doesn't include it. This is my structure system. So make sure that the reactions are kind of external forces, okay? So if you treat in that way, that you can solve this problem. So for the detailed the calculation procedure, please talk with my TA, and he will cover the solution procedure for the compliance method. So now let's talk about the second example here. The second example. Yeah. So let's talk about the second example. So I have a cylinder of copper, and then inside this copper cylinder, I have steel. In the copper tube, I have a solid steel cylinder here. So the combination of these two systems resisting an external force P applied to this structure system. Okay, so let's check the system. Okay, so first we have to simplify the structure system. I have a rigid plate, and then I have a copper, and I have steel. This is one-dimensional system. And then I have here, I have a reaction. And then I have applied load P. So this is my default choice of my coordinate system. Okay. So first we have to consider distribution of a displacement system. This is amount of displacement, and this is x coordinate. Because here this is support, okay? This is support. The displacement should be equal to 0, and then I have a non-zero displacement here. Let's say this is, I want to call B and A, point B. So I have non-zero nodal displacement UB, and this is my the change of the displacement field. So we can calculate the strain very easily. UB is equal to UB minus 0, because here, okay, divided by the length of the member. The length of the member. This is a strain. Then we can calculate the stress value. Sorry, we have to drop this. We have to drop the E. Okay, this is strain. And then my stress is elastic modulus times, and then strain, isn't it? But we have two different materials. That's why the stress of copper is elastic modulus of copper times strain. So times the strain is same here, UB divided by the length, okay? And then stress of steel is elastic modulus of steel times UB, point B, divided by the length, okay? So now let's check the force equilibrium. Now this is my free body diagram. So I want to consider this free body diagram, okay? So with respect to this free body diagram, so I have a rigid plate, and then I have to consider a concentrated force here, and I have copper and steel, Okay, the option 1, this is the stress field, sigma C and sigma S. And how about option 2? The option 1 and option 2. Sigma C and sigma S. So which one is correct? Option A. You still don't understand the nature of the stress. Well, so many students are thinking option A is correct, but option A is not correct because because this guy that compresses the material. Look at this. So I have material in this free body diagram. Okay, even with respect to this free body diagram, this traction, compress the material. Okay, to compress the material. This sign is negative, okay, negative. So now, for these unknown quantities, I want to deal with default sign, okay, default sign. That's why this is the correct choice, okay. This is the correct choice for the consideration of the force equilibrium for this free body diagram. Okay. So if you understand this, for any calculation, I need to have a local coordinate system. So now let's use this local coordinate system just for educational purpose, okay? Sum of all the forces in downward direction should be equal to 0, okay? So I have positive P and then positive this. So stress in copper. And then we need to multiply the area of copper plus stress of steel and the area of steel. So where is the information of normal stress for the copper and steel? The normal stress, information of normal stress for the copper and the steel is here, okay? So let's plug these expressions into this equation. So everything is systematic, one by one, okay? You don't have to worry about it. Everything is, one by one. Then this is equal to what? So P plus the length of the member, the length of the member, the elastic modulus of copper, the area of copper, times nodal displacement at point B, plus elastic modulus of steel and the area of the steel divided by length and the nodal displacement should be equal to 0. So we have only one unknown here, right? So we have only one unknown. We have only one unknown in this equation, isn't it? Oh, by the way, I forgot that it was 0 here. It's 0, okay? I have only one unknown, the nodal displacement UB. So then we can determine the nodal displacement. So once I determine the nodal displacement, I can determine the normal stresses and the strains, blah, 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 whatever, okay? Isn't it right? It's very easy, right? Very easy and systematic. And then let's visit the same problem. We can handle the same problem by using the compliance method. The key point in the compliance method, we have to decompose the structural system. So first, I have what? I have, this is original structural system, copper and steel. And then we want to consider this, the sum of the structural system in this way. Okay, first, so I want to consider the copper plus steel. Okay, copper plus steel. And then I have force P, and then I have force P. So if you check the force equilibrium, okay, if I check whether it satisfies the principle of superposition, the superposition of system 1 and the system 2. Okay, let's check the force here. So if you check here, I have P plus P is equal to P. That doesn't, that violate the force equilibrium condition, isn't it? So we shouldn't use that. Then what do? So although we don't know the contribution of the copper and steel to the resistance of external force P, but we can introduce an unknown here, a ratio. say let's introduce factor k. So which means the copper carries a part of load P identified by the factor coefficient k. And then how about here? The external load should be equal to 1 minus k, isn't it right? 1 minus k. This is my structural system. Then sum of kp plus 1 minus kp becomes load p. Okay? So then we can calculate the nodal displacement u of first one. And then we can calculate nodal displacement of the second system. Then what is the condition? Because in the original system, they are one piece, okay? They are one piece, which means ui, the displacement of point system 1 should be equal to displacement of point 2, the system 2, okay? Using this condition, we can determine the coefficient k. Then that's how we can finish our analysis in the compliance method. So because this method is given in the textbook, I teach you, but this procedure is kind of obsolete. Yeah, it's better to use the displacement comparability directly to tackle the statically indeterminate structural systems. But the compliance method is still useful to derive some analytical form of expressions or the simplification. Superposition principle, the principle of superposition in 우리말 중첩의 원리. This is very important to understand or analysis of linear elastic system. So we will revisit the principle of superposition later. So let me start my lecture here. So again, today we have TA class, okay? Please join the TA class too. Do you have any questions? So next time we'll talk about non-mechanical deformation, okay? Non-mechanical deformation. So let me start my lecture here.